In this section, we're going to be looking at medians and altitudes. To start off with, we're going to look at a term called a median of a triangle. A median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. So here in the diagram, you can see that the line has one endpoint at a vertex at the top and one endpoint at the midpoint of the opposite side. Now we're going to look at the theorem 5.8. The name of the theorem is concurrency of medians theorem. The theorem states the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So here in our diagram, you can see that we have three different medians of a triangle drawn. The first median, if we look at the one drawn from vertex D, you see the line that's drawn from vertex D all the way to point J. It bisects the side FE, so it has them split into two even parts. And then the distance of D to C equals 2/3 of D to J. And this concept is similar for the other medians of the triangle. So if we look at EC equals 2/3 of EG. And similarly, FC equals 2/3 of FH. In a triangle, the point of concurrency of the medians is the centroid of the triangle. Now we're going to look at an example that requires us to find the length of a median. In the diagram, XA equals 8, and we have to figure out the length of line XB. When we look at the diagram, we can see that A is the centroid of triangle XYZ because it is the point of concurrency of the triangle's medians. So based on the concurrency of medians theorem, XA equals 2/3 XB. And because we know the value of XA, we can go ahead and substitute that in. So 8 equals 2/3 XB. And now what we want to do is we want to isolate XB, basically solving for it. So we want to go ahead and multiply both sides by 3/2. When we multiply the right side by 3/2, it becomes 1 XB. And when we multiply the left side by 3/2, we get 24/2, which is 12. So 12 equals XB. And now that we know the length of XB, it is 12. Now we're going to look at another theorem, theorem 5.9. The title of the theorem is concurrency of altitudes theorem. The theorem states the lines that contain the altitudes of a triangle are concurrent. The lines that contain the altitudes of a triangle are concurrent at the orthocenter of the triangle. That's what the point of intersection is called, the orthocenter. The orthocenter of a triangle can be inside, on, or outside of the triangle. So here in our example, we can see that the acute triangle, when you draw the altitudes, you just drop it straight down from the vertex. So if you look at the top vertex, you're just basically drawing that line straight down. It does not split the bottom line in half. It just goes straight down and creates a 90-degree angle with the side opposite. So the acute triangle has the orthocenter inside. The right triangle has the orthocenter on the triangle, and the obtuse triangle has the orthocenter outside the triangle. Now we're going to look at a concept summary of special segments and lines in triangles. So the first one all the way to the left, we can see that the lines are made based on perpendicular bisectors, and the point where they all intersect is called the circumcenter. The next one is angle bisector, so basically all the lines bisect the angles, basically splitting them equally in half, and the point where they intersect is going to be called the incenter. The third one is created using medians, which is basically from one vertex to the midpoint of the side opposite, and the center of that where all the lines intersect is called the centroid. The final one that we have all the way on the right is created by altitudes, basically dropping a line from the vertex down to the opposite side, creating a 90-degree angle with the opposite side. And the point where all of these intersect are called orthocenter.